Now that we know a little bit about complex numbers and how square root of minus 1 can be written and works, we're going to look at solving equations where we have solutions or roots that are not real. So when the discriminant of our quadratic is negative, is less than 0. So this is counting on from the questions in our examples. Just the next bit, this is number 5. So solve the equation z squared plus 9 equals 0. Sorry if you heard Alexa during that. I think she got a little bit excited when I said examples. I think she felt like I was talking to her. Never mind. So z squared plus 9 equals 0. So hopefully here we can see if we subtract 9 from both sides, there's going to be no solutions to this quadratic because we can't square something and get a negative value. Well, not previously, but now we should be able to deal with this. So we can square root both sides here. We still get plus or minus square root of minus 9. But now we can cope with this because we can split this into root 9, root minus 1. Root 9 is 3. And root minus 1 is I. So we get plus or minus 3i. So we get imaginary solutions for this. You could complete the square if you wanted to. You can do all kinds of things on these questions, although completing the square is not favourable here actually because we don't have a z term, do we? But we'll come on to questions. In fact, the next question where we can do this. So it works pretty much the same way as it would do with normal quadratics, but instead of panicking when we see this, not panicking, but not expecting to any solutions, we can now go a few steps further and we can actually get imaginary solutions for this. So let's have a look at the next one, question 6. So this is solving z squared plus 6z plus 25 equals 0. And remember, with all these kind of questions, you can always check your discriminant. And we're using z rather than x here. We tend to use z to represent complex numbers. But if it's x, it still works exactly the same way. So if we look at b squared minus 4ac for this, we get b, which is remember these all correspond to the coefficients of the quadratic if we were to write like this. So b is 6, a is 1, and c is 25. So b squared minus 4ac, we're going to get 36 minus 100, so we get minus 64. So this tells us straight away there's going to be no real roots to this quadratic. Okay, there's no values of z in the real world that will satisfy that. But we can use the quad formula to solve it, and since we've worked out b squared minus 4ac, let's have a look at that, and then we'll look at completing the square. So our z values will be minus b, so minus 6, plus or minus the square root of b squared minus 4ac, which we've already worked out, all over 2a, which is 2 times 1. So we get minus 6 plus or minus root minus 64. We can write as root 64 root minus 1, and hopefully you're getting a bit more familiar with that. So here we get minus 6 plus or minus 8i over 2. Minus 6 over 2 is minus 3, 8 over 2 is 4. So we get minus 3 plus or minus 4i, so minus 3 plus 4i is one solution, minus 3 minus 4i is one solution. And you might start to notice some things, start having to think about what's going on here if you notice any kind of pattern emerging. You might not, don't worry, but we'll come on to it in a future video. Or we can complete the square. So let's have a look at that because it's good practice to see how it works. So with this one, remember when we complete the square we want to half the coefficient of this. You want to make sure you've got coefficient of 1 of z squared at the start. So a, the coefficient of your quadratic, the highest power in the quadratic is 1. And then we halve the coefficient of z, so z plus 3 all squared. And remember, I'd always check as you go along, square this out, check you can go back to the previous step. So square z squared, times them together, 3 times z, 3z and double it is 6z, but we're going to get a plus 9 that wasn't there, so we need to minus 9 to balance that out. And the 25 tags along, tidy things up. So 25 minus 9 is 16. Okay, now from here, we can minus the 16. Normally, this would be ugly and we wouldn't like it and it wouldn't work, but we can now square root this. Still get plus or minus, but we get root minus 16. And this is root 16, root minus 1. So notice how there's always that kind of pattern of getting that -1, whether it be here. Sorry, my pen stopped working. So whether it be here or here. Oh, the pen is playing up here, sorry. So we're always getting that root -1 kind of separated out, so we can put our I in and we can use the square root of the other number. So there we go. So this will be plus or minus root 16 is 4, so 4i and then -3 from both sides. And we get the same two options as we do doing it via method 1. So two nice ways of doing it. Completing a square is good if you've got no coefficient here, or the coefficient is 1 in front of the z squared. So I'm trying to point it out, but the pen stopped working again. So when the coefficient here is 1, completing the square is a nice way of doing it, but we can always use the formula if we want. And if we've already worked out the discriminant to check things, then you're already kind of, you've done the trickiest part of the formula there. There's question 5 and 6. Let's do one more, question 7. So this one was just asked slightly differently. So the equation z squared plus bz plus 11 equals 0, where b is a real number. That's all this means. B is a member of the real numbers. Hopefully you remember your set theory. Has distinct non-real complex roots. Okay, so it's telling us that there's no real roots. So as soon as we see no real roots, we should know that implies that the discriminant of this is less than 0. And we can sub in b is actually b, so that's quite nice. So we get b squared minus 4a is 1, c is 11, less than 0. So we know for these values of b, we're going to get no real roots. Okay, this is a quadratic inequality. So we're going to need a little sign diagram, critical values, in order to solve this. So if we just think of this as with an equal sign, then we can get our two roots. So 44. So root 44, which is root 4 root 11, or 2 root 11. So there are critical values. I'll just go up here to write the sign diagram and finish the question. So our sign diagram, we're going to draw our line out, part of it anyway. Draw our line out. That's terrible. I'm going to use a ruler. There we go. And then the pen stops working. Oh, there we go. Much better. Okay, we've got our two values. Obviously, minus 2 root 11 is going to be a small value than plus 2 root 11 on our number line. You can draw, it's a b squared is a positive coefficient, so it's a minimum. It's terrible. It's quite hard on the laptop, sorry. And we want less than 0, don't we, according to this? So we want the bit underneath. We want this bit, so sandwiched between the two values. So we want b to be less than this and greater than this. So continuous interval, there's no break from here to here. So we can write it as a combined inequality. So for those values of b, this quadratic at the top here has complex roots, so the roots are not real. Outside of those values, you'll get your real roots. And that's solving equations using our newfound knowledge.